Okay, so now we're back for the last installment of this wonderful series of videos. Okay, so now we're looking at work. Actually, after everything else you've done, this will be easy. All right, so work is, in this case, like a formal term, something that can be measured with a specific unit. Okay, and it is um, how much energy essentially goes into moving an object a certain distance using a certain force in a certain direction. Okay, so it says here work is done when a force causes an object to undergo a displacement. Now remember, a displacement is a distance in a particular direction. Okay, so it's a vector quantity. Okay, so the work done is just the calculation is just you take the force vector and you find the dot product of the force vector and the displacement vector. Okay, from this picture, we have the displacement vector. We can see it's horizontal. All right, so we find its magnitude. We have our force vector. We can see it's raised by an angle of theta off of the horizontal. So I just plug those details in and I can calculate my work. And when I'm using work and I'm calculating it, okay, my displacement is measured, its magnitude is measured in meters, okay, and the force is measured in newtons, okay. So when I use work, I have the basically newtons times meters, and that is called a joule. So 1 joule of work is using a force of 1 Newton to move something 1 meter. Okay, so here I have example number 7. All right, so I have dragged my object 5 meters horizontally. Okay, and I've also used a force of 30 newtons, and these are both horizontal. So it's just asking to find the work done. So if I have my object here, I'm moving it, okay, horizontally 5 meters, and I'm applying a force. These are just, I just made up these scales, but I guess generally this should probably be 30, so it should be 6 times as much, okay, but it's not the same unit. Okay, so this is a force of 30 newtons. This is a displacement of 5 meters, and they are both horizontal. So if you think of the theta between the two, it's going to be 0. All right, degrees. So when I figure out the work, I'll put W equals, okay? You're just going to be finding the vectors here, okay? So I'm going to pause the video, you do the calculation, and then come back. Okay, so here I am back. So I just took my magnitude of the force, which was 30, magnitude of the displacement, which was 5, cos of 0. Sorry, that should not have a little theta thing in it. Okay, this should just be 0. And so when I find the cos of 0, it's going to equal 1. So I just have 30 times 5. So my work is 150 and the unit is joules. So that's it right there. Okay, so try the next one. Now this one's slightly different. This is another toboggan question. So you can imagine a child. I'm just going to draw a box for the toboggan. Okay, so here's the toboggan on the ground. Okay, a child is pulling the toboggan 100 meters. So this is the displacement, and it's moving along the ground, so it's horizontal. So this is 100 meters, okay? And they're pulling with a force of 200 newtons that is applied at an angle of 40 degrees to that horizontal. So here's my force vector, 200 newtons, okay? And it's applied with an angle of 40 degrees, okay? So my work, I'm just gonna do my dot product. Okay, so I'm gonna pause this and you guys can come back. Okay, so here I am back. So you should have found that when you plugged everything in, all right, remember we need the magnitude of the force, the magnitude of the displacement, and the angle between, the cosine. So I'm going to have 200 times 100, and my angle is 40, so I'll multiply by the cos of 40, and I round it to one decimal place. I get 15,320.9 joules. Okay, that's it. All right. So let's move on to the next page. I am going to ask you to make one change into this question, okay, because I want to look at the difference in work dragging an object the same distance across the ground as dragging it up a ramp. So I'm asking you, please change this to 5 meters. So we're going to see the work when we drag it flat on the ground 5 meters. And then we're going to see how the work changes. Is it going to increase or decrease when we apply the same force, the same distance, but up a ramp? Okay, so our work, we're going to have to calculate two pieces. So I'm going to have to calculate the work for the first part of this action. So the first part, I'm dragging it across the level ground. And then I stop and I start dragging it up a ramp. Okay, so let's just put this into pictures so you can see. So here's my object. Okay, I'm dragging it along the horizontal for 5 meters, and it says my force vector is 20 newtons, and I am using the force vector as 50 degrees to the horizontal. Okay, so this is going to be work number one. So just take a moment and figure out work number one. Okay, so what you should find here after you plug all that in and do your calculations, okay, I'm using a force of 20 newtons along 5 meters at an angle of 50 degrees. So you'll find that my work done is 64.3 joules. Okay. So now let's draw the diagram. So this is going to be a little bit trickier to draw this diagram. Okay. Because the idea is that now you're shifting to a ramp. That's not very 30 degrees. Let's say our ramp is like this, and it says our ramp is 30 degrees. Now, when I draw my box, my object, it's going to have to sit on this ramp. Okay, so my displacement is no longer horizontal. It follows the same angle as the ramp. Okay, so that's why I changed this to 5, because I want to move at the same distance, and I want you guys to think what's going to happen. Okay. Now, it says here that the force remains the same. So that means still it's 20 newtons, but more importantly, it's still 50 degrees to the ground. So if you think about this angle, if that's horizontal to the ground, the force, even if I apply it just in line with this displacement vector, that will be 30 degrees to the ground. Okay, so I still want it to be 50 degrees to the ground. So I have to take into the account the ramp kind of increases what would be an original angle of 0, increases it by setting it on the ramp, increases it 30 to 30 degrees already. So I have to think what's left. And so the resulting angle, to still have it 50 degrees to the ground, the angle between the displacement vector and the force vector is the difference between the 50 degrees to the ground and the 30 degrees already added by the ramp. So in this case, be really careful, because your theta is not going to be 50, it's not going to be 30, it's actually going to be the difference between those. So it's going to be 20. Okay, so make sure you understand that reasoning. All right, so now I want you to figure out work 2 and think, okay, I'm doing it in a different situation. And imagine yourself, you're trying to pull something along level ground and then suddenly you pull it up a ramp. Do you think this work is going to be more or less? Well, let's see. Okay, so I've set up my formula here. So you can see the force is still 20 newtons, the displacement is still 5, but instead of applying the force at 50 degrees to the displacement vector, I'm only applying it at 20 degrees. So you've probably done this calculation already, but you can see when I make this calculation, okay, even though the angle is smaller, the cos of the angle is bigger. Okay, so I'm going to have 94.0 joules. So it's more work, which I mean makes sense logically. It's more work to pull something up a ramp. Okay, so in order to get the total, so therefore the total work, okay, I'm going to have 64.3 joules plus 94.0 joules, okay? So therefore my total work is going to be 158.3 joules. Okay, good. All right, so one more to go. All right, so here, this is actually, I mean, relatively speaking, an easier question. So I'm given a force vector right here algebraically. Okay, so this is a position vector showing the magnitude and direction of the force. Okay, and then it says it's being applied, excuse me, it's being displaced from point A to point B. So the displacement vector you're going to have to calculate. It's going to be AB, okay? And then that measurement, you're told is in meters, okay? So rather than use the dot product that is the magnitude of F times the magnitude of D times their cos of their angle, you're going to use the algebraic definition of the dot product. Okay, so before I give anything else, I'm just going to have you go ahead. So please pause and give it a try.